So yes, we know that we know a lot about fusion in the vertebral column of tetrapods. So for example, we know the sacrum in mammals, and we know the highly fused vertebral column in birds. But we also have a fused vertebral column in chondrichthyans. The anterior part of the vertebral column fuses in the batoids, in the skates and the rays. And we see an example of this in Raja clavata, the thornback ray indicated by the red arrow. And this is known as the synarcual. So we're interested in the synarcual in placoderms, and we've described the synarcual in the tictodonts and also in some arthrodires. You're looking there at Cartilage McLaughlini. And one of the things we're very interested in placoderms and also in chondrichthyans is how does this fusion occur in the synarcual? How does the fusion of the vertebral elements occur to create this element? There are a few ideas. So first of all, we could have vertebral fusion as a result of a failure of somatogenesis, where somatogenesis is somite development in the embryo from anterior to posterior, from pre-Semitic mesoderm, or PSM at the caudal end of the animal. The image on the far left shows these somites very nicely differentiating from the pre-Semitic mesoderm. So it's the ventromedial somite that differentiates into the sclerotome, and it's the sclerotome cells that migrate around the notochord and the neural tube to form the vertebrae. So again, just referring to that image on the left, if we didn't have the differentiation into somites, as you see just down here, we could have just a single sheath of cartilage forming like the synarcual. So that's one idea, that you have a failure of this somatogenesis, and that creates the fusion that you might see in a synarcual. There could also be tissue transformation between the vertebrae. So this is known in the mouse, in the pig, where you have the intervertebral discs ossifying in the sacral region to form the sacrum, just here at the bottom of the screen. One other possibility is that you just have ongoing cartilage deposition. Here we're looking at the synarcual of the electric ray, Narcini, again a member of the batoids, and anterior is to the left. Here's the synarcual, and right here are some vertebrae that are fusing into the synarcual. So perhaps the cartilage is just continuing to develop in that region, fusing up the vertebrae, or perhaps the cartilage program has been reset to deposit cartilage there to fuse up these elements into the synarcual. There was a very interesting idea presented this year by Kate Criswell and her colleagues. So they were looking at embryos of the little skate, Leucoraja. And what they found in the upper two images is that initially you get cartilage sheaths developing, so shown in the purple and the blue. And it's the breakdown of this cartilage sheath that results in the formation of the individual vertebral elements. So applying that to what I just showed you in Narcini, maybe instead of having vertebrae fusing here, we have the synarcual as the remnant of this cartilaginous sheath identified by Criswell and her colleagues. And what we're seeing here is just the breakdown of that sheath to form these vertebrae. So instead of fusion, the synarcual is the result of separation into different elements, but not the synarcual itself. So we have all these different possibilities for the formation of a synarcual. So I'm going to leave chondrichthyans now and focus for the rest of the talk on the placoderms. So as I said, we've already described the synarcual in tictodonts and also in some arthrodires in Cartilage, but I want to focus now on the synarcual in Dunkleosteus. But not quite right away, because I do have to talk to you about Cartilage. So Cartilage McLaughlini, again, is an arthrodire that shows a synarcual. This is what the typical unmodified vertebrae look like. They're perichondral bone, and the neural and hemal arches, importantly, have this very distinctive circular base to their arches. This is the synarcual of Cartilage, and anterior is to the right. And what we found was that we could see within this synarcual structure these discrete vertebral elements. These are still visible, including that very distinctive rounded arch base. So our idea was that because you could see these discrete and distinct elements still preserved within the synarcual, that somatogenesis must have progressed normally, the sclerotome, the sclerotomal cells, the development of the vertebrae, And it was after this that these vertebrae became fused into the synarchual. So in these placoderms, and this is what we also saw for the ptyctodonts, that semitogenesis progressed normally. But now to move on to Dunkleosteus. So this is the specimen that we're studying from the Cleveland Shale of Ohio. We have the anterior trunk shield to the left, seen in internal view, and I've marked the position with the asterisks in the upper right. The head shield is also associated with this specimen, but it's not included in this picture. So here's the synarchual extending along the bottom here in position. And so because we're looking at the internal surface of the trunk shield, if we just flip all that over, we think what we're actually looking at here are the upper neural arch elements. Now, in this region here, posteriorly, again, anteriors in that direction, indicated by the red arrow, we see two sets of normal vertebrae, two sets of normal neural arch elements. They're very similar to ones that have been described for a closely related Arthrodire, Osteus. And what we see here, again indicated by the red arrow, is this very distinctive scoop-shaped surface, articular surface. So it's that scoop-shaped, it's very hard to say, scoop-shaped surface that is articulating to the notochord. As we move anteriorly, we move into the synarchual, and I think you can see that the vertebral elements are being modified. We were particularly interested in this area that I've marked as the transitional zone between these unaltered vertebrae and the very altered vertebrae in the synarchual. We were able to CT scan this, and again, looking at the normal vertebrae here, very clear this scoop, again articulating to the notochord. But as we pass towards the synarchual, there's a median wall here for the arch base that is quite strongly developed. It's actually scooped here as well. But as we move into this area, what we see is that median wall is crushing. It's breaking down. We think it's becoming resorbed. So we move through the transitional zone, and when we come to this vertebrae here, there is some element of that median wall left, but it's almost missing. And then by the time we get to these vertebrae, that median wall has been completely lost. That scoop has been completely lost, and the vertebrae are very flat. So from posterior to anterior, the vertebrae shape is changing quite substantially. Now, if we look at this area in a little bit more detail, again, we have the remnants of some of that median wall here, but crushed, remnants here, but almost completely lost, and then completely lost here. So the vertebrae are becoming flattened, but we're also seeing new bone being deposited between the modified vertebrae. So that's indicated by the red arrows, with the black arrow just here showing where those vertebrae, those flattened vertebrae, are becoming fused together. And so we see a first layer indicated by the red arrows that's being deposited between these flattened vertebrae. So is this perichondral bone? Because again, the arch elements themselves are made of perichondral bone. But that would imply that there's ongoing development of cartilage between the vertebrae and then the deposition of this perichondral bone. Another alternative is that it's simply membrane bone deposited in the tissues between the vertebrae, and this implies that cartilage doesn't necessarily have to form. Internal to that first layer of bone, we have a second layer of bone developing. It seems to begin at these nodules. Now, these may be points of development of the bone. So here we have some nodules and some bone developing around them. And these nodules are quite interesting because as we go into the synarchual, they form quite distinct multiple rows between those flattened vertebrae. But again, as in Caurolepis, as in the ptyctodonts, these vertebral elements very clearly remain distinct within the synarchual. So again, the vertebrae develop normally, semitogenesis occurs normally in both the placoderms and in the ptyctodonts and in the placoderms as a whole. But again, how does this fusion occur? Well, as I just mentioned, it could be that possibility of ongoing cartilage deposition or a resetting of the cartilage program followed by the deposition of perichondral bone. Or perhaps a bit more parsimoniously, it's just membrane bone being deposited. Membrane bone doesn't require the cartilage program to be restarted all over again, but it would still function to fuse those vertebrae together. But I think what's important to point out is that what we see in Dunkleosteus doesn't correspond to what Kate and her colleagues were seeing in the little skate. So again, they were seeing the cartilage sheath breaking down to form the vertebrae, and I suggested that perhaps in chondrichthyans like Narcini, the synarcule is just the remnant of that process. But in Dunkleosteus, we're seeing not a breakdown to form the vertebrae, we're seeing bone deposition to fuse the vertebrae together to form the synarcule. So that's what we're thinking about with respect to the synarcule and placoderms. Dunkleosteus is important because it's really given us the most developmental detail about how the synarcule forms in placoderms, again, a fossil group over 350 years old. It may be quite different from what's going on with the synarcule and chondrichthyans, but that's a bit of work that we're doing at the moment. So just some conclusions. In the placoderms, we have recognizable vertebral elements in the synarcule, and this suggests that semitogenesis proceeds normally. In Dunkleosteus particularly, we have the deposition of at least 2 layers of bone, which suggests that the vertebrae are fusing together, not becoming separated. And the deposition of membrane bone is perhaps the most parsimonious alternative because it doesn't require a cartilaginous precursor. Continuous cartilage formation is not required, and it's not required to reset the program for cartilage development. So just a few acknowledgements, and particularly to Richard and his team for organizing SVE PCA this year. Thank you very much.